Hello and welcome to our fourth and final video for week 2 about proofs. Today we're going to prove some properties of transpose, and I'm going to walk you through kind of my messy process of figuring out a proof and kind of, open up my brain a little bit, I guess, and give you some insight into what I was thinking as I was trying to write the proof, where I stumbled and where I wasn't quite sure. Before we jump into this, I did want to remind us of what the definition of transpose is. So kind of in layman's terms, we switch the rows and the columns, right? So A transpose is going to be the matrix Aij transposed. And what that means is we're going to take that Ij and we switch the order to Ji. You know what, while I'm writing reminders up here, let me also write a reminder about matrix multiplication. So if I have a matrix A times B, then that's going to be Aij times Bij, and that's going to equal the summation over K of Aik Bkj. And what's going to be important for us later is that these K's kind of line up. So that's a little bit of where we're going to be headed. Before we can get there, let's state our properties of transpose. Remember that when we state our theorems, we have to make sure we know the conditions that are applying before we can, know what the properties are. So for this theorem, we're going to have A and B be matrices. So that the indicated operations can be performed. And we're going to let K and P be elements of R. So K and P, again, are scalars, and A and B are our matrices. Then 1. Suppose I have A transpose, and then I transpose it. What do you think is going to happen? So I have a matrix, and I switch the rows and the columns. So rows become columns and columns become rows. And then I do that again. I switch the rows and the columns. So I have, columns become rows and rows become columns. That's just going to undo what I did in the first place. So if I transpose the transpose, I get back to where I started. It's kind of like, right, if you negate a negative, you're going to go back to the positive. So that's what's going on here. For our second property, suppose I have a product. So I have A times B, and then I transpose it. Can we distribute transpose? What do you think? That would make life too easy, y'all. So we can't really distribute it, but we do have an equal to B transpose A transpose. So if you want to transpose a product, you can, but you have to reverse the order of those two matrices. And because matrix multiplication is not commutative, that matters. So we can't just write A transpose B transpose. And lastly, our third property is going to have to do with a sum, and scalar product. So if I have Ka plus Pb transpose, this time it is like we can distribute transpose. So we're going to get K times A transpose plus P times B transpose. So these are our 3 properties of transpose. And the one I'm going to walk you through is number 2. So again, this is going to be a messy process. So we're going to make lots of mistakes, and that's okay, because that's how the process of proofwriting, works. So I'm going to clear some space, and then we'll begin our attempt. Okay, so before we get started with this attempt at a proof, I do want to mention a couple things that have helped me just as a human being, attempt this. So I'm the sort of person who's a bit of a perfectionist at times. And what I found is that if I try to write a proof perfectly from beginning to end, writing nice and neat and clean and easy to see, what that means is that my thoughts end up being cramped because my writing is small and neat. So my thoughts kind of remain small. So what I have to do if I want to, ideate and come up with ideas and try things out and feel free to make mistakes, I have to be a mess. So I have to be able to write nice and large. I have to be able to erase easily and kind of go back and forth that way. So I would encourage you when you're attempting your proofs process, give yourself that freedom. So when I first started this, I, would write on computer paper really big. And then I was like, man, I'm killing all the trees. So I bought myself a small whiteboard when I was in graduate school to kind of help me think and process my thoughts when I was writing proofs and stuff. So that's why a lot of math teachers will have a whiteboard or a chalkboard in their office, because it just helps to write it out big and visualize it and, try and process what's going on. So that's what we're going to do here. We're going to start out. We have to decide which side of this equation to start out with. So I'm going to start with the left. Usually, the left is a good place to start if they seem about the same. And so I'm going to start out with AB transpose. Now, in this process, just for simplicity's sake for this video, I'm not going to be writing my reasons as I go along. I'm going to be stating them. But typically what I do when I'm doing this is I might do like a little abbreviation or something, or I might fill them in at the end. I do recommend that you jot down your reasons so that if you do have like a problem throughout, the proof, when you look at it again, you can be like, well, what was I thinking? What property did I think I was applying? But just for simplicity's sake and because of, limited space and stuff, I'm not going to do that. So, okay. Our process so far has been, we start out with our matrix notation, we expand, it starts out expanded, we condense it, and then we expand it back out again. So let's try that here. That was my first approach. So I said, okay, this is going to be Aij times Bij transposed. And so this is a product. So I'm going to use my product notation over here. So this is going to be the sum of Aik Bkj transposed. Now, at this point, I'm thinking, okay, so ultimately, I know that I need B times A, right? That's what I'm trying to get to. So in my path to that, if I'm going to have that sum here, this order is important because multiplication is not commutative. So I know that I'm going to need to have, instead of Aik Bkj, what I'm going to try and get to is something like Bik Akj, right? So I want to try and reverse so that instead of the K coming second on the A, it's going to come first. And then similarly, instead of the K being first for B, it's going to come second. And I'm going to need this so that I can write B times A. So that's how I'm using the statement of the proof to kind of guide my thinking and say, okay, I got to this point, now what, right? So I know that transpose is going to switch the indices. So if instead of this being, the ikth element of A, it were the element of A transpose, then that would switch those indices. So I'm going to rewrite this as the sum over K of AKI transpose and BJK transpose. And now, because these are real numbers, I can swap them, right? So this is going to be the sum over K of BJK transpose, AKI transpose. And then I said, okay, so this is now B transpose A transpose multiplied together. So I said this is now B transpose A transpose transposed. And this is where I was like, gosh darn it, that's not what I wanted. I didn't want that. I don't want this fancy transpose out here. Okay? I don't need that. I just need the B and the A alone. And is this right? Because now I'm suspicious. So my thought is I must have done something somewhere to make a mistake. And I did. I spent some time looking at this and I was like, I can't figure it out. I know this is not where I want to get, and it's going to be wrong because I know this should be B transpose A transpose, not the transpose of that. So I made a mistake somewhere and I don't know where it is. So when that happens, and I can't kind of get out of that lock of the pattern that I'm in, start on the other side. So if I have this on a sheet of paper, I'll set it aside so I have it for later. But really, I'm just going to erase that. Nothing to see here, nothing to see. And let's start all over again. So this time we're going to start with B transpose A transpose. But I'm going to follow the same process. So I have my big matrices. I want to they're nice expanded out, and I want to bring them together so we have real numbers so that we can bring them back out again. So this is going to be the BIJs transposed, and this is going to be the AIJs transposed, because that's our notation. Now, if I have the transpose, that means that I can change the order of the indices. So that's what I'm going to do. So I can transpose each of these individually. So this is going to be BJI, and this is going to be AJI. Okay. Okay. So we're multiplying matrices together now. So this is going to be the sum over K. Now, because my indices are swapped, I have to keep them swapped here. So this is going to be BJK, and then we have AKI. And now we want to do the same thing as before, because now we want to have AB, not BA. So that trick that we used before is going to be helpful here, because I'm going to write this in terms of the transposes, so I can again switch the indices and we get it in the proper order. So now this is going to be the sum over K of BKJ, AIK. Oh, those are each the transposed, right? Because if I'm switching the order of the indices, I have to, this is now the kjth element of B transpose, not of B. So then, because we are commutative, we have AIK, or A transpose IK, I'm sorry, and then we have B transpose KJ. Now, which is A transpose B transpose. Because now I've got the ikth element of A transpose and the kjth element of B transpose. So shouldn't that be that? And that's not where I wanted to get to. I wanted to get to this. And I know matrix multiplication doesn't commute, so I'm really suspicious that B transpose A transpose might equal A transpose B transpose when I'm trying to prove something different. So what the heck is going on here, right? So is this trick of kind of switching these and writing those in terms of the transpose, is that going to work? I mean, I feel like I need to have that work because I need to be able to switch these order in order to get this order switch to happen. But something about the way that I'm going about it is wrong. There's something wrong in this process and I can't figure it out. So what I did when I was, going through this was then I went back and I started with this side again and tried to avoid what I had done before and did literally the same thing. And then I came back and I did this again and did again, literally the same thing, trying not to. It's one of those like, okay, well, let me go one step more, right? And let me go one more step. And there's something I'm being sloppy with that I shouldn't be sloppy with. And I don't see where it is. So when I was doing this problem, I had to stop. I had to set it aside. I'd been working on it for like, I don't know, 30 minutes to an hour. And I was like, I got to stop it. I got to go to bed. It's late. So I'm just going to keep going in circles. So that's what I did. And sometimes you just need your subconscious to process and to work on what you were doing and look at it again with fresh eyes. So that's what I did. And here's what I came up with. So I was feeling pretty confident that this index switch that's happening is going to be important. It's going to be necessary because there's not really any other way that we can switch the order of things. So I know that this part's probably going to come up and I'm probably going to need it. So what I did when I looked at this again was I said, don't do this first. So far in all of the proofs we've done, we've gone immediately from this into that IJ notation. And I said, what if that's the issue? What if that's where my problem is? So figured everything out again. Made a new pot of coffee, set it all up. And I said, okay, I'm going to start here. Fresh eyes, fresh eyes. And I said, you know what? I'm not going to jump into that IJ, into that like little a and little b notation right away. Instead of thinking of this as A and then B all transpose, then transpose. What if I thought of this as just like, this is the matrix C. Let C be AB, right? So I could let C equal AB. And then I could say, all right, so AB transpose is C transpose. Okay. And then that's going to be the CIJ, which is transposed, which is CJI transposed. Okay. And then I thought I might be able to do something with that. So just instead of writing it in terms of C, I just kept the A and the B there. So I said, okay, this is the same as if I were to take the product AB and take the ijth entry of that and then transpose it. So I started thinking of this as a whole instead of as separate pieces. Then, instead of immediately jumping to the, I shouldn't have had a transpose here. Instead of immediately jumping to, the AIJ, in this definition, basically, instead of jumping to multiplication, I said, let me deal with the transpose. So if I transpose this, that I and that J are going to switch. So this is not the ijth entry of AB, it is the jith entry of AB. So now that I have the jith entry of AB, let's apply this definition. The thing that's going to be different is because this is the jith entry, I'm going to have a J here and an I here instead of an I and then a J. So this is going to now be the sum of AJK BKI. This is over K. Now I'm in a situation where I can try to apply that trick that I had done before, right? Where this, I can represent this as like A transpose and this is B transpose. So I'm going to write this as the sum over K of A transposes K jth element and B transposes I kth element. You can switch the order because real numbers are commutative. So we get B transpose IK and A transpose KJ. Oh, and this is looking promising now because I have B transpose and A transpose, and my indices are in the order I want them to be in. So I have the ith element IK, and then KJ. I need that to be able to write this as B transpose times A transpose. And that's where we needed to go. Hooray, that's what we wanted. So the trick to this one, there were two, and I had one of them, and I kept going in circles because I was doing the wrong process first. So the trick to this one is indeed, you know, applying the index switch to be able to switch the order of the multiplication. But the other trick is don't go to multiplication too fast. The other trick is apply this transpose first so that you switch your indices, then do the multiplication, and you can get to where you need to be. So I think in those previous iterations, what was going on was I was ending up with like JK, KI when I really needed and I wanted IK, KJ. So that order of the indices was what was messing me up. So once I do this whole process, then I celebrate, huzzah! Now I'm going to go in and I'm going to clean this up. So now I'm going to take this to my, you know, official piece of paper. I'm going to put it in my notes packer or wherever. And when I do that, I'm going to indicate my reasons along the way. So still makes me happy that I figured it out. So going from here to here, this is just a notation. So we can represent the ijth element of AB. Then we applied the transpose by switching the indices. So this is the definition of transpose. Then we took that product and we wrote out the jith element of that product. So this is the definition of matrix multiplication. Then I wanted to switch the indices here. So this is again, the jkth element of A is the same as the kjth element of A transpose. So this is our definition of transpose. Then these are real numbers, so we can commute real numbers. So we have commutative property of real numbers. And then now I had this product that I wanted to get to here, and that's our definition of matrix multiplication. And there we go. Finally, at long last, we finished this proof. So I will mention even this process here, I cleaned up a little bit. You know, I didn't go through the agony of doing things multiple times, but that's going to happen, especially if your head's in a lock. So if you notice that, if you notice like you just keep going in this like same path and you need like a break, take a break, because the inspiration is not going to come if you just keep hitting your head against the same wall. So I was hitting my head against the same wall of immediately jumping to matrix multiplication notation instead of dealing with this transpose definition first. So sometimes it just takes time away to gain that perspective. So again, don't think that, you know, if you have trouble doing proofs, like they don't magically come to you right away. There's nothing wrong with that. That's the process. That's what writing a proof feels like and is. So it takes a lot of experimentation. It takes a lot of back and forth. It takes a lot of, you know, collaboration. So if you get stuck, ask a classmate and say, look, here's what I'm doing. Can you see what I'm doing wrong? I keep getting stuck here. And if they're like, yeah, beats me, I'm doing the same thing, right? Then you can kind of bounce ideas off of each other and, you know, talk to me or come to Oxars, whatever, and try and figure out where's the hole that you need to poke to shine some light on there. So, so that's, that's our heavy end to this week. Next week, we're going to be talking about like now that we have our operations, you know, all set, we're going to be talking about, we don't have matrix division, so how can we solve an equation if we have multiplication of matrices, right? So if I have my system of equations, AX equaling B, I can't divide by matrix A. So how am I going to isolate X? What am I going to be able to do to solve that equation? so that I can ultimately solve my systems of equations. So first we're going to talk about invertible matrices. So we're going to talk about the inverse of a matrix, which kind of makes sense, right? It really, when you're solving an equation, you're not dividing, you're multiplying by the reciprocal. So you're multiplying by the multiplicative inverse of something. So we're going to see if we can find multiplicative inverses for matrices that will allow us to solve. And then we're going to see basically, is there a shorter process to being able to find that inverse? Because spoilers here, the process of finding an inverse, despite its standard process, is going to involve row reduction. It's going to involve just doing a lot of row reduction, and as we've seen, that can be a little time consuming. So we want to see if there's something that's a little bit speedier to get us along there. And of course, now that we've done some proofs, we're going to see them all the time. So be ready for that too. So I hope you have a wonderful day, and I'll see you next week. Bye.